You might have seen pictures or videos of people floating effortlessly in the Dead Sea. If you think it's easy, try reclining in a similar position in a freshwater pool. Most likely, you will sink. Do you know why? Let us look for the answer in Archimedes' principle. We shall understand this principle through an activity. Here is an object whose volume is 130 cubic centimeters. Weigh this object using a spring balance. Its weight is 10 Newton. Now, take a Eureka can. Fill it with water up to the spout. Under the spout, place a measuring cylinder on a weighing scale. Now gradually dip the object in water. Observe that water starts overflowing through the spout and the reading in the spring balance registers a continuous fall. Once the object is completely immersed in water, no more water flows out and the balance shows a steady reading. Note this new reading. It is 8.70 Newton. Hence, we can say that the object appears to be lighter inside the water. This weight is called its apparent weight in water. The object appears to have lost 10 minus 8.70 equals 1.30 Newton weight. We have previously learnt that this apparent loss in the weight is equal to the buoyant force that acts on the object. The buoyant force is therefore 1.30 Newton. Now, measure the volume of water collected in the measuring cylinder. It is 130 cubic centimeters, which is equal to the volume of the immersed part of the object. Note the weight of this displaced water. Interestingly, it is also 1.30 Newton, which is equal to the buoyant force. But are these two quantities always equal? Let us confirm by repeating the activity using a different liquid, say glycerine. Note that although the object again displaces 130 cubic centimeters of liquid, but this time the weight of the displaced liquid is 1.60 Newton, which is more than before. This is because the density of glycerine is more than that of water. Now from the spring balance, note the apparent weight in glycerine and calculate the apparent loss in weight. It is 1.60 Newton. Thus, the buoyant force acting on the object this time is 1.60 Newton. Isn't it interesting that in this case too, the buoyant force is equal to the weight of the fluid displaced? This relation was discovered by Archimedes and is called Archimedes' principle. It states that when an object is partially or completely immersed in a fluid, it experiences a buoyant force whose magnitude is equal to the weight of the fluid displaced by the immersed part of the object. Now, the weight of the fluid displaced is equal to the mass of the fluid displaced times the acceleration due to gravity, g. If the density of the fluid is ρ, then the buoyant force is equal to volume of the fluid displaced into ρ into g, which is equal to volume of the immersed part of the object into ρ into g. This equation clearly shows that the buoyant force depends only on the volume of the immersed part of the object and the density of the fluid. The same can be confirmed from the previous activities. In water, the object experienced a buoyant force of 1.30 Newton, while in glycerine it was 1.60 Newton. This is because the density of water is less than that of glycerine. Thus, we can infer that for the same object, the denser the fluid, the larger is the buoyant force acting on it. Does the buoyant force depend on the density of the object immersed? We can observe and answer by taking another solid object having the same volume of 130 cubic centimeters. but a different density and immersing it completely in water. Note that the buoyant force remains the same as before, that is 1.30 Newton. Can you now use Archimedes' principle to understand why it is possible to float effortlessly in the Dead Sea? Due to the presence of a large quantity of salt, density of the Dead Sea water is larger than that for the pool water. Thus, the buoyant force in the Dead Sea is also larger, even larger than your weight. Hence, it pushes you up to the surface and keeps you afloat, while in a swimming pool, you sink. Summary: when an object is immersed in a fluid, it experiences a buoyant force equal to the weight of the fluid displaced by its immersed part. This is called Archimedes' principle. The buoyant force is equal to volume of the fluid displaced into rho into G, which is equal to volume of the immersed part into rho into G. For the same object, the denser the fluid, the larger is the buoyant force acting on it. The buoyant force depends only on the volume of the immersed part of the object and the density of the fluid.